Okay. Again, weight and normal force are the two common forces that you'll be encountering in dynamics. Okay. So first things first is let's try to distinguish between weight and mass. Although in sometimes we try to interchange these two, but specifically they are different quantities. They're very different quantities. So what is weight? How do we define weight? Well, weight is the Earth's gravitational force. Earth's gravitational force. Gravitational force exerted on an object. And again, the unit, since it is a force, so since it is a force, it is measured in newtons. Okay? And mass, on the other hand, is the amount of matter an object is made. And if you can see here, it's measured in kilograms. And one more thing, uh, weight is a vector quantity and mass is a scalar quantity. So weight or force of gravity on the surface of the Earth is calculated by. So this is near the surface of the Earth or just the surface of the Earth. The weight is given by the formula. We use FG for that. So it is just given by the mass multiplied by the acceleration due to gravity. Acceleration due to gravity. Okay? Or that is just, in short notation, that is just mg. And the g that we use is 9.8 meters per second squared. And just like any other forces, it's a vector quantity and it's always directed downward. So again, conventionally, we try to use downward as the negative direction. So therefore, we try to use that one. The negative also, FG is negative. Okay. So again, in our case, weight is just calculated by multiplying the mass, but it should be in kilograms. So if you can see here, your mass must be in kilograms, and G is in meters per second squared. Okay. So two distinct characteristics between, or the difference between weight and mass is that weight varies with location. Because if you can see, Fg is dependent on G. But G is not necessarily constant, even on Earth. Different location on Earth will have a variation in the value of G. Actually, G is affected with altitude, okay? Although in our case, as long as we are near the surface of the Earth, we just use that particular value. So weight varies with location, while mass is constant. Constant means that wherever you are, your mass is the same. Okay? So let's say, for example, your weight on Earth and moon and the moon and on the moon, the Earth and on the moon are different. Okay, but your mass is the same. So mass is the same, so that means constant. It would not change, but the weight would be different on different location. So try to think of that again. Your mass would be the same regardless of your location. So as long as you're not eating or discharging anything, so your mass here would be the same wherever you are. However, your weight could be different. Okay, so that is one of the main difference between the two, aside from being a vector, weight as a vector, and mass is a scalar quantity. This is just a scalar quantity. So that's why mass doesn't have any direction. Okay. So you try to calculate your weight on Earth. Okay. So like for example, myself, I'm around maybe 60. I haven't. So if my mass is around 60.0 kilograms, so G on Earth would be 9.8 meters per second squared. So my FG is just M times G. That's 60 multiplied by 9.8. So my weight is around 588 newtons. So actually, if someone asks for your weight, I don't know if they will accept that value because, well, we try to make mass as our weight, right? But strictly speaking, mass and weight are two different quantities. So if your mass is around 60 kilograms, so your weight should be 588 newtons. So you would say Newton. Okay, my weight is 588 newtons. But I know that in most cases, what they mean is that they want for your mass. Okay. Okay, let's take example number 2. The acceleration due to gravity on moon is 1/6 on Earth. What is on Earth? So in comparison, moon has the acceleration due to gravity only 1/6 compared to the acceleration due to gravity on the Earth. Find the weight of a 350 kilogram piano on the moon. Okay. So again, in this case, be careful with this one, mass. Okay, the mass of the piano is given. So you know that mass would not change. So that means that the mass of the piano on Earth is, I'm just gonna use mass on Earth is 350 kilograms, which is just equivalent to the mass on the moon. Okay. Again, remember mass would not change. So therefore, its mass, regardless of its location, would be 350 kilograms. Now we want to get the weight. Weight is given, but that is weight on the moon. So that means that that is my FG on the moon. Since I want to get the weight on the moon, that means that I'm using mass on the moon. But again, I know that regardless, should just be the same, and G on the moon. Okay. However, well, you're given the value of your mass. Mass on the moon is given as that, but you don't know the value of G. It's not directly given in the problem, but you're given that the acceleration due to gravity. Remember that G is acceleration due to gravity. Most kids or most students will just say, oh, gravity. Well, it's actually acceleration due to gravity. That's why the unit is meters per second squared. It's an acceleration value. It's 1/6 on the Earth. And you know that the Earth, G on Earth is 9.8 meters per second squared. So therefore, the G on the moon is equal to 9.8 divided by 6, 1/6, right? So therefore, if you want to get the weight of the object on the moon, you have 350 kilograms. Again, it wouldn't change, times 9.8 over 6. So weight of the piano on the moon would be equal to around 2.7 times 10 to the power of 2. No, sorry, this is not the one. That should be 570 newtons. Okay. So comparing that one on the Earth, if you want to get the FG on Earth, that would be 6 times of that, 6 times 570. So that would give you around 3,400 newtons. So on Earth, that's quite heavy, but on the moon, it just becomes around 570 newtons. So that is why you can see the sensation on the moon in the movies, that seems like you're floating. But actually, that is due to the fact that the gravity there is smaller. So that means that you fall there at a lesser rate. The Earth, you will be falling 9.8 meters per second in every second. So that means that the rate of change of your velocity here on Earth is around 9.8 meters per second in every second. That means that if you're just dropping yourself on Earth, after 1 second, your velocity becomes 9.8. And then 2 seconds after, it becomes twice of that, 19.6. Okay? Then so on and so forth. So you have an increasing. But on the moon, 1/6 of 9.8 is around 1.6. That's around 1.6. So that means that on the moon, you'll just be falling at a rate of 1.6 meters per second in every second. So that's quite slow compared to the Earth, right? So yeah, that's how you see it. That's why they try to have that sensation if you are in space or on the moon, that you are floating. Well, it's just that the gravity there is smaller. So if the gravity is smaller, that means that you will be falling also there at a lesser rate compared to the Earth. Any question on this one? Yeah, it's just a matter of using the formula that you have for the weight equation. Again, later on, I think that would be in Physics 12. We will not be talking about Newton's gravitational law, because that is more a specific equation for gravitational force. This is more the simplified version of that. Again, this is only true for near the surface of a planet or of an object or a massive object. Okay, let's take number 3.
Oh, I have a question, Mr. Villar.
Yes, yes.
Why is it 9.8 rather than negative 9.8?
Uh, yeah, that would be, you can use the negative sign there. In this case, I'm just trying to, yeah, might as well be more consistent with that one, like downward, okay?
Okay.
So down. Because anyway,
Okay.
it's always directed downward, right?
Mhm. So
Well,
would it matter in the equation if I were to put negative or not a negative?
Uh, uh, it would, in the sense
As
that
long as I would have like the final, it would just say like down.
yes. So
Okay.
if you put downwards, well, yeah.
Okay.
Especially, yeah, I always try to say that if you're asking for a vector quantity, you need to place the direction, right? Yeah,
Mhm.
just to be consistent with that one, just weight, again, weight is a vector quantity, so it should be both magnitude and direction. So, however, in weight though, weight, we know that it's always directed downward. So down, its
Down.
direction is,
Okay.
yep.
Thank you.
Okay, you're welcome. Okay. Uh, Marlu has a example number 3 has a mass of 60 kilograms. If his weight on the sun, if he didn't burn up, is 1.6 times 10 to the power of 4 Newton, determine the acceleration due to gravity of the sun. So this is the weight and the magnitude of its weight, and its mass is given by this. We want to get the acceleration due to gravity on the sun. So if you're gonna write you're given the mass 60.0 kilograms, and then Fg of 1.6 times 10 to the power of 4 newtons. Again, direction of weight is always down, or actually, specifically speaking, that should be towards the center of the sun or towards the center of the earth. And we want to get the g, the acceleration. So we're given the weight, and again, this is assuming at the surface of the sun. So our starting equation would be Fg times mg. So g is just equivalent to Fg over m. So that would be 1.6 times 10 to the power of 4 all over 60. So g is equal to, so if you're going to divide that one, that would give you answer of 2.7 times 10 to the power of 2 meters per second squared down. If you can see, that's around 270. That's 270 meters per second. Well, that is also expected because the sun is much uh, massive compared to the Earth. So 270, that's around what? How many times? 30 times? More than 30 times 10. Yep. Around more than around 30 times the acceleration on Earth. Well, again, that is to be expected because the sun is also quite massive. Okay, but uh, you're gonna learn this one more if you're gonna talk about the Newton's gravitational law, and that would be part of physics 12. So in our case, this is just a more general. I like the simplified version. Again, this is only applicable near the surface of the Earth or near the surface of a particular planet. The more specific expression is given by gravitational law of Newton. Okay, we proceed to normal force. Just change the some of the notes there, just to be in sync with our definition of the normal force. Normal force is the contact force exerted by a surface on an object, well, solid surface usually, on an object. Okay, so if you can see, we can relate it to the third Newton's law, that it's just also the reaction force. So if you are exerting a force on a surface, that surface exerts back a force. And yeah, specifically we call that one as the normal force also. Okay, so normal force. So that's how we define normal force. So let's take this example number 4 here. Determine the normal force experienced by a 45-kilogram person standing on a horizontal surface. So you have, if this is your surface here, you have an object, or you have the person standing. Okay, so determine the normal force experienced by the 45-kilogram person. Well, this particular person will exert a force on the surface. At the same time, the surface will react. So the force exerted by the surface on the person. Okay. If you can see here, if you will be asking for the normal force, well, again, this would be my normal force here. This is Fn, the force exerted by the surface on the person, right? So now, if we want to know that normal force, we try to examine the forces acting on person. Okay, so we want to know what are the forces acting on the person. So if this is my person here, what are the forces acting on that particular person? Well, we know that a person on earth will always be acted upon by gravity. Call that one Fg, which is equivalent to mg, mass times the acceleration due to gravity on earth. And well, if you can see, the surface also exerts a force on the person, and we actually just call that one as the normal force. So the normal force is upward. So the force being exerted by the surface of the person is just called the normal force. And again, any object on earth will always be subjected by the force of gravity. So gravity of the, and in this particular case, he's just standing, is not jumping or what. So therefore, this is at rest. Okay, the object or the person is at rest. So if the object or is the person is at rest, So if he is at rest, that means that the net force acting on the person would be 0. Again, how would you know that one? Because he is at rest. Again, that is first Newton's law. This is the first law of Newton. Okay, so now if you can examine what are the forces on acting on the object, well, it's given by Fn plus the negative of Fg is equal to 0. Again, it's negative, Fg is negative. Again, when you take the sum of the forces, you have to be careful with the sign convention. In our case, again, upward is positive in this case, downward is negative. So that would be Fn plus the negative of Fg is equal to 0. Or, if you can see here, normal force, therefore, the magnitude of the normal force is just equivalent to the magnitude of Fg. If you're gonna, well, algebra thing, so plus F on both sides, it gives you Fg. So the normal force, therefore, in this particular case, is just equivalent to the mass times the acceleration due to gravity, which is 45 multiplied by 9.8. So the normal force is just equal to 4.2 times 10 to the power of 2 newtons. Then this is upward. Okay. So again, actually, you can already identify by just looking at the figure. If this is not moving, that means that these two forces should be equivalent, equal in magnitude but opposite in direction. But it's always good to start your solution or practicing your solution this way. Like you're gonna, well, because here, if you can see, if the net force is equal to 0, it doesn't mean that you don't have any forces acting on the object. So that's what I'm trying to point out here. Net force is equal to 0 does not mean no forces acting on object. Okay, it does not mean, because if you can see, you are actually have two forces is acting on the object. You have Fn and Fg. You have two forces acting on the object, your Fg and Fn. So when you say that net force is equal to 0, so this is an example, that's why I show it this way. It does not mean that you don't have any forces acting on the object. You actually have two. It's just that when you try to take this algebraic sum, when you take the sum of your forces, it gives you 0. Okay? It doesn't necessarily that you don't have any force acting on the object, especially here on Earth. Well, again, you're always subjected by the force of gravity. Okay? Any question on this one here? Hopefully you will not, if you can see this particular expression, you will not take this one as, oh, I don't have any force acting on the object. Well, actually, there's no particular problem wherein you can set that one as you don't have any force. Obviously, if you don't have any force acting on the object also, you can set that one to 0. But then again, for most problems, you're talking about problems that is happening on the surface of the Earth or what. So therefore, you have at least gravity there. But remember, if the object is not moving, there must be more than one force acting on the object. Because if not, you have an unbalanced force. you know what happens if you have an unbalanced force, right? So it's either be, it's accelerating. It would be accelerating. Okay. And by the way, another thing, if net force is equal to 0, there are two state of motion of your object. It's either at rest or moving with a constant velocity. So in this case, it's not moving, so therefore their forces balance out. But same thing is true if the object is moving with a constant velocity. So if the object is moving with a constant velocity, that means that the net force acting on that object is equal to 0. So any question with example number 4? Any question? No. Yeah, hopefully you can drill this one out, that net force is equal to 0 does not mean that you don't have any other forces acting on the object. Okay, let's take number 5. Calculate the normal force acting on a 13.5 kilogram package resting on an inclined plane at 30 degrees. Okay. So remember, in this case, you have, it's angled off. It's not resting horizontally on the surface. This is around 30 degrees here. Okay. So therefore, it's not as simple as the normal force is equivalent to the weight. Well, that is only true if the object is lying horizontally on a surface. But in this case, it is somehow in an inclined plane. Okay. But still, you need to remember the definition of what is a normal force, right? Normal force is a perpendicular force perpendicular to the surface. So if I'm gonna examine the free body diagram of this one, okay, it's resting, so that means that not moving. Okay, it is not moving. Again, I know that it is not moving because of that word. It's resting. So I'm gonna represent the box as a point. Again, just do that one. You can do that. And then examine what are the forces acting on the box. Well, for one, I am quite sure that there is gravity, and gravity is always downward. So regardless of the position of your box, FG is always downward. Okay, that's my FG. What else? Well, by definition, again, normal force is a force, the force exerted by the surface under the object, and it is always perpendicular. So that means that my Fn is not going upward, but somehow also angled off. It should be here. Or that 90 degrees. Yeah, it would be something like that. This should be my Fn. Normal force. Again, normal force is, this is my normal force. That one there. Again, it's perpendicular to the surface. So let's say, for example, this is my imaginary surface. So remember that this is, let's say, oops. Okay, happened. Oops. Okay, I think I moved my, okay. Well, okay, there you go. Okay, so my surface is, remember, it's inclined. So if this is my surface here, so again, my surface is somehow angled off. Let's try to draw my Fn. My Fn, if this is my surface, okay, the black one is my surface. So normal force is again just a force that being exerted by the surface on the object, and its direction is always perpendicular. So if you can see, I hope that's perpendicular enough. That means that this is 90 degrees here. That's 90 degrees. Okay, this is 90 degrees. There. That will be my Fn. Again, Fn is not always upward. Remember that if the object is lying in an incline, somehow the normal force is also be like this. It's not going straight upward. Again, the reason for that is by definition, the direction of your normal force is always perpendicular and away from the surface. So that's what happens here. Okay, and then what else? I have two forces there. What do you think would be the other force? Did I miss any force here? Can anyone tell me if there are more forces that I need to draw? Anyone? Hello, are you there? Anyone? Or would this be mine? Am I only talking about two forces? Hello?
I think they also have a friction here.
Okay, great. You have friction. Where do you think is the direction of friction? Where?
I think is up, like 30 degrees up.
Okay, yeah. Because remember, friction is, its direction is parallel and opposite in the direction of the acceleration, barring any net external force, right? So in this case, if you don't have any friction, this object, if F is equal to 0, that means that this object will be moving downwards here. So that would be its acceleration down there. However, since it is resting, there must be some sort of friction. And the friction is parallel to the surface, and its direction is opposite. So this would be my friction. Yeah, upward for your yeah, that would be friction. And actually, those are the three forces. And that's it. That would be your three forces acting on this 13.5 kilogram package. But the question is, we need to find the normal force. So the question mark is this one here. How would you find that particular value? Remember that in this case, the normal force is no longer equal to the force of gravity or the weight of the object. However, if you can see here, D, if you're gonna somehow also tilt your coordinate system, you can have, in terms of parallel and perpendicular to the surface, you can have, or you can create two components of your weight. You have this one here, and I'm gonna call this one as the component of the weight that is parallel to the surface. Okay? Parallel to the surface. If you can see, that is parallel to the surface. And a force that is perpendicular. So you have the component of the weight. This particular component of the weight is your perpendicular weight. Okay. Again, why did I say that it's perpendicular? Well, if you can see, that's 90 degrees. Okay. So if you can see here, somehow Fn and Fg perpendicular are on the same components. They are perpendicular components. So therefore, these two are related. And actually, since this is not moving, I would say that the magnitude of the normal force is just equivalent to the magnitude of this, as well as the magnitude of the friction is the same as the magnitude of my parallel force. So now, I'm gonna do is I'm gonna get what would be this, because Fg is given by mg, and I can solve for that. That is just 13.5 multiplied by 9.8. So Fg is equivalent to around 132 newtons. So I will just not round that one off. I'm just gonna use that one later, that the gravity or the magnitude of weight is equivalent to 132 newtons. But then again, this one here is tilted in a certain angle. So I want to solve for Fg perpendicular and Fg parallel. How would I do that? Well, I need to locate this 30-degree angle. Where do you think would that be? There are two choices. Okay, I'm gonna call this one as the first one, and this one is the second one. So first, then this is the second one. Where should I put the 30-degree angle? The first one or the second one? Anyone? Where do you think is the location of the angle? Hey. Anyone? Okay, before you answer that question, can you turn on my cam as well as your cameras? Can you turn on your cameras? Yeah, we can use a pendulum. Like you have an object here, right? It's something like this. It's on top. Horizontally, that would be the form, right? However, if I gonna have something that is that would be 90-degree angle, if I gonna have something like lying over there like that. So if this is parallel to the surface, if the surface is not angled off, let's see what happens. This is 90 degrees, right? It's just moving down. It's just down. So where do you think is the angle when I try to move this one up, if I'm gonna move this one up, which particular angle, remember that the inclined is this angle here, right? So where of the two angles, remember that if I'm gonna move this one up, this just continues downward, but the angle here also moves and this angle here moves, right? So if I'm gonna move this one up slowly, which of the two of the angles that is corresponding to this one, the angle here or the angle here, the first one or the second one? Anyone? So if I'm gonna move up, right? If this is completely perpendicular, that's 0 degrees, that's 90 degrees. Can you see that one? Can you picture that one out or no? It's hard. It's hard to see. No? Like, it's very hard to. Okay. If we're gonna do that, right? This is horizontal, or the horizontal plane. This is the surface. I'm not trying. If I'm gonna incline this one, this is gonna move up, right? This is gonna move up. Okay. So see what happens if I'm gonna move the surface, the horizontal surface, up or down. Which of the angle? Remember that slowly, if you're gonna move this one up, the angle is smaller and then gets bigger and bigger and bigger, right? So I've shown you which part. If I'm gonna move this one up, remember that this will always be pointing downward, just like your weight, because weight is always downward, right? But if I'm gonna move this one up, remember initially, what is the angle here? That's 90 degrees full, right? That's 90 degrees. They're perpendicular, correct? Can you see that one? That's 90 degrees. This angle, like the angle, this straight line and this line here is 90 degrees, correct? Correct? That's 90 degrees. However, if I'm gonna move this one up, slowly, the angle here decreases, right? It's no longer 90 degrees. But the other one, as this moves up, is it not that, again, this is the straight line, the other one is here, that is perpendicular to your surface that is moving up. Well, is it not that the angle that corresponds to this angle here is the angle in the first one? Can you see that one, the first one? Like if we're gonna move this one up, see, this is downward, the angle here increases at the same amount as the increase of this angle here. Can you see that one or no? It's very hard. It's quite hard. Hello? Did you get that one? That the angle would be, the angle of 30 degrees would be this angle here. This should be the 30-degree angle. Can you picture that one out, that the angle is 30 degrees there, or that's quite hard to see? Is that would be the angle? Can you see that one? Why is it that it should be in the first part? The angle is 30 degrees or no? Hello? The 30-degree angle, that's quite important later on, because not all the time you'll be dealing with a horizontal plane. Sometimes it will be inclined. So it's very important for you to locate that corresponding angles or that angle there. Because if you can, well, if you miss the location of the angle, obviously your perpendicular force there and the parallel force would be different. It will also be interchanged. So if you cannot see how you get that particular angle, that's quite hard. That's the first step. Because again, if you just try to guess, well, that would be really hard. Hello? Can you see that one, or it's very hard to visualize? No? Anyone? Yeah, maybe we can talk about that one more later on. Yeah, maybe I gonna devise something from the protractor. Maybe perhaps it's much clearer if we're gonna do that. Yeah, I'll be doing, yeah, maybe once we have the in-person lesson. Although I know that on Tuesday, okay, you know that on Tuesday we'll have the retest, right? Unit 2 retest. So everyone should prepare for that. Okay, you'll be given the same formula. So just make sure. So same thing, free falling and projectile motion is part of it. And you'll be given the graphs also. Okay, the graph. Remember, position time graph and velocity time graph, as well as your acceleration time graph. So yeah, remember that. Okay, maybe for now, I'm just gonna finish this one up, and we're gonna revisit this particular example once we see each other. Okay. Yeah, maybe I can devise something from a protractor. Okay. So we'll just again just try to remind me later on that we're gonna revisit this particular example here. Again, if you miss the location of the angle, that would also flip your like the perpendicular and the parallel, the perpendicular force and the parallel force. So going back here, if you can see, the main question is the normal force. Hopefully, the only thing here that you need to remember also is that if the object is inclined, the normal force is no longer equal to Fg. Okay, so the normal force is not equal to your magnitude of your weight. So if you can see here, Fn is equivalent to the magnitude of the normal force is equivalent to the perpendicular component of the weight. And if you can see there, you can create a right triangle from that angle. If you can see, this is just a right triangle there. So therefore, you can use trig ratios to get the perpendicular component of your weight. And if you can see here, that perpendicular component is the adjacent side of the angle, okay? So if you can see, I'm just concentrating on this part here. So that is just, maybe I'm just gonna redraw that one again. So is it not that this would be your right triangle? This is your FG perpendicular, and then this is your FG. Okay, on there. So this is your 30-degree angle. So if you can see, this is the opposite side. This would be the adjacent side. And again, this would be your hypotenuse. So this would be the hypotenuse. So if you're solving for FGL, that is just the adjacent side. So that would be cosine. So that would be cosine 30 degrees is equal to adjacent side is your FJ perpendicular all over FG. So therefore FG perpendicular is given by FG cosine 30 degrees. Okay, so that means that the normal force is just equivalent to FG cosine of 30 degrees. So we know that FG is given by that, so I'm gonna substitute it, and that's 132 cosine 30 degrees. And if you can see, that would be the magnitude also of the normal force, which is equal to that would be 115. So that would be 115 newtons. That would be away from the surface. Remember that the direction of the normal force is always away from the surface.